Alright, in 7.1 we're going to be exploring exponential models. So the exponential function is y equals a base to a power x. So when we graph exponential functions, we look at three special points. Our first one, we have -1 and then 1 over whatever our base is. The second one is 0, 1. And this point is actually our y-intercept. And then our third point is 1 and then whatever our base is. So if we look at an example, we're going to graph y equals 2 to the x power. So in this case our base is 2. So our three special points, we have -1 and then we have 1 over our base. So we have 1 over our base, which in this case is 2. Our second special point is 0, 1, or the y-intercept. And our third special point is 1, and then our base, which is 2. So there's our three special points, and let's go ahead and plot those. So we have -1, 1/2. We have our y-intercept at 0, 1. We have a point at 1, 2. So it's going to look something like that. And if you wanted to find another point, let's say x equals -2, we could plug it in. So we have y equals 2 and x is -2, so 2 to the -2. When we work with exponents, we know that if we have a negative exponent, we can make it positive by flipping it and bring it to the bottom. So that's the same thing as 1 over 2 to the positive second power, which is 1 over 2 squared is 4. So that tells you there's a point at -2, 1/4. So if you went -2 up about 1/4. Alright, so this graph gets very close to the x-axis, but it doesn't touch or cross. So when we look at our domain, we're always looking at our x's. So we're looking x-axis, we're going forever in the left direction because we have an arrow, and we're going forever in the right direction. So our x's are never going to stop, so our domain is all real numbers. So our range, well, if it's not going to touch or cross, that means it's never going to cross this x-axis, which means your y is never going to be negative. It's always going to be in the positive direction. But if it doesn't cross it, our y is never 0. So your range is going to be y is greater than 0. Alright, so the x-axis is what we call a horizontal asymptote. So this means the graph will get close, but it will not, in this case anyway, touch or cross it. So if we talk about exponential growth and exponential decay, I'll go ahead and draw our little graph over here. Alright, so exponential growth. This is when, as x increases, our y also increases. So if we start over here, we know if we go to the right, our x is increasing because our x's are getting bigger. And if we know if we go up, our y's are also increasing because your y's are getting bigger. So our growth, as x increases, our y is also going to increase. So that's exponential growth. And when we talk about exponential growth, if our base is greater than 1 and our exponent is positive, then it's exponential growth. And if our base is between 0 and 1, with a negative exponent, it's also exponential growth. So for example, if we had y equals, let's go 1/2 to the negative x. Well, your 2 down here really has a power of 1, but we never write that. So we can bring it to the top, but if we bring it to the top, it's not going to be positive 1 anymore, it's going to be 2 to the negative 1. So we have 2 to the negative 1 still raised to the negative x power. Well, when you have an exponent raised to a power, that's when we multiply our exponents. So we're going to have y equals 2 to the negative 1 times negative x is just positive x. So our base is 2. So our base is greater than 1, and our exponent is positive x. So our exponent is positive, therefore it's exponential growth. Alright, so if we have exponential decay, as our x increases, our y decreases. So that's going to look something like, we know if we go to the right, our x's are getting bigger, but it's going to come down and keep going down because our y is decreasing. So as we go down, our y is decreasing. As we go to the right, our x is increasing. So this is our exponential decay. So when we talk about our base in this case, if our base is greater than 1 and the exponent is a negative, it's exponential decay. Or, let's put an or in there. If our base is between 0 and 1, with a positive exponent, it's exponential decay. So off to the side, for example, if we have y equals 1/2 to the positive x. Well, we said over here 2 really has a power of 1, but we can bring it to the top, but instead of positive 1, now it's going to be 2 to the negative 1, and that's still raised to the x. So if we have a power raised to a power, you multiply your exponents. So that's really 2 to the negative x. So in this case, our base is 2, which is greater than 1. Our exponent is negative x, so if we have a negative exponent, it's exponential decay. Alright, so our y-intercept is at 0, 1, unless there is a stretch or a compression. Or if we have a vertical shift. So our x-intercept is at 0, 1 unless there's a stretch or compression or a vertical shift. So if we have a stretch or compression, you're going to multiply the 1 and your y-intercept at 0, 1. You're multiplying that 1 by whatever your stretch or compression is. So in your homework assignment, Math Excel, they may want the number, but don't forget you always write your answers in order pair, especially on the test or the quiz. Alright, so if we do an example, the first thing we want to know is if we have exponential growth or exponential decay. So the first thing we look at is our base. In this case, our base is 1/2. Well, if our base is 1/2, that makes our base between 0 and 1. Then we look at our exponent. If it's positive x, we have a positive exponent. And you can flip it back over. So we're looking at these two case scenarios. Our base is between 0 and 1. And since we have a positive exponent, it's going to be exponential decay. Alright, so part B. They want us to find the y-intercept. In order to find the y-intercept, we're going to sub in 0 for our x. So we have y equals 3 times 1/2 to the x, and we're plugging in 0 for x. So we have y equals 3 times anything to the 0 power is 1. So 1/2 to the 0 power is just 1. So y is going to equal 3 times 1, which is 3. So you write it as an ordered pair. So we said our x was 0, and we found our y to be 3. So in this case, our y-intercept is at 0, 3. Alright, so the next example, all it's asking is what is the base of 1/2 to the negative x? Well, your base is 1/2, which is between 0 and 1. And then you look at your exponent. Your exponent is to the negative x, so you have a negative exponent. So we just labeled that. Alright, so let's do an actual model or an example. So we have a decay model. This works for money, and it'll work for population. But in this case, we're going to talk about money. So we have a of t. This is a function notation. So your a is the amount of money present after t time has passed. So what that means, if you have a of 4, that would represent the amount of money after 4 years. So the amount of money after 4 years. Alright, so to the right of the equal sign, our little a, that is your initial amount. Our r is the rate of growth if it's positive. So if it's positive, it's growth, or decay if it's negative. And we're going to use the decimal version, not the percent. So for example, if we're given 7%, we're going to use the decimal version, so your r would be 0.07. So we moved our decimal places 2 to the left. And then the last thing, our t up here, t represents the time that has passed. So we're going to use this model to do this example. Alright, so it says that we're going to invest $1,000 on our 18th birthday in an account that pays 5% annual interest. Your mom is going to invest $4,000 on her 50th birthday in the same type of account, and we want to know who has more money on their 65th birthday. So we're using our a of t equals a times 1 plus r to the t. Alright, so let's talk about us first. So our a, their initial amount, is what we're putting in right away. So we're going to invest $1,000 on our 18th birthday. So our initial amount is $1,000. So next, let's look at our rate of growth. We have growth because we're positive. We're seeing how much we're going to invest. So we have 5% annual interest. Well, we said up here we don't want percent, we want it as a decimal. So 5% as a decimal would be 0.05. So your rate is 0.05. Now we're going to find our t. T is time that has passed. So if we want it on our 65th birthday, but we put the money in that account on our 18th birthday, we're going to take 65 minus 18 to get 47. That tells you that 47 years has passed from your 18th birthday. And now we're just going to plug it in. So we have A of our t, which we said t was 47. So that's the amount present after 47 years. And that's going to equal our A, our initial amount, which is 1,000, times 1 plus our rate. Well, our rate we said as a decimal was 0.05. And that's to the t power, and our t is 47. Alright, so let's start simplifying. So let's simplify our inside first. 1 plus 0.05 is 1.05, still raised to the 47th power. And that's going to equal 1,000 times, if you take 1.05 to the 47th in your calculator, you're going to get a big decimal. I'm just going to write quite a few out. So 9.905971092. And if we take 1,000 times this big decimal, we're going to get $9,905.97. So, starting on our 18th birthday, we put $1,000 into the account. And after 47 years, we have $9,905.97. Alright, let's see how much the mom has so we can compare. So the mom, her initial amount, she put $4,000 in. So her initial amount is $4,000. Her rate is going to be the same as ours because it says in the same type of account, so 5% annual interest. 5% as a decimal is 0.05. And her time that has passed, we started 65th birthday, minus she put it in on her 50th birthday. So 65 minus 50 would be 15 years. So let's plug it into our model. So we have A of our t, which is 15, and that's going to equal our initial amount, which was 4,000, times 1 plus our rate, which is 0.05 still, raised to the t. Well, mom's is 15 years. Let's start this off. So we have 4,000 times 1 plus 0.05 is 1.05, still to the 15th power. So we have 4,000 times, if you take 1.05 raised to the 15th in your calculator, you can get 2.078928179. 4,000 times this decimal will give you $8,315.71. Well, now we can compare the two. So looking at the two, on your 65th birthday, who's going to have more money? Well, you can see that you are, because you have $9,000 and she has $8,000. So I have more money on my 65th birthday than mom does. So plug it in and compare them. Alright, one more. we're going to work backwards. We're still using this model up here. So we want to know, when will we have 10,000 in our account? Well, since it's asking when, we don't know our t yet. That's what we're going to try to find. So if we have 10,000 in our account, that's going to be our final amount. So we have 10,000, and that's going to equal, since we're talking about us, our A stays the same, so our initial amount is still 1,000 times 1 plus our rate stays the same, which is 0.05, raised to the t, and we don't know what that is. So we wanted to know how much we have, or how long it'll take us to get 10,000 in our account. So in your calculator, we had talked about whatever is to the left of the equal sign is going to go in your y1. So your y1 is going to be 10,000, and our y2 is going to be to the right of the equal sign. So our y2 is going to be 1,000 times 1 plus 0.05, and we're going to raise it to the x power, since our calculator knows x and y, not t. So if you get your calculator, in our y1, we have 10,000. In our y2, we have 1,000 times 1 plus 0.05 raised to the x. And we can hit zoom 6, and we're going to have to adjust our window a bit. We're not going to be able to see it right away. Because if we have a line at 10,000, that's going to tell me that we have a horizontal line way up here at 10,000. So let's go to our window. Let's change our Y max with about 10,500. And let's extend our X max out a bit so we can see. Let's do 30 and hit graph. So there's our line at 10,000. And let's see if, that doesn't look like we're going to be able to see it. We're going to have to extend way out. It's going to meet somewhere up here. So let's make our X max bigger. Let's see if we can hit it at 100. There we go. Alright, so we want that intersection. That intersection right there is going to tell us our year, or the time it's going to take for us to reach $10,000. So the intersection, we have to go to second calc, and we want number 5 for intersection. So second calc, and we want number 5, and bring your little cursor over until you can see about where it intersects, and hit enter 3 times. So our intersection, when our y is 10,000, or when we have $10,000, our x, which is our time, is 47.19. So if we're talking about years, we're going to leave it as a whole number, so 47 years. So t would be 47 years. So that tells us after 47 years, we're going to have $10,000 in our account.